In this mini lecture, we will derive the compressibility corrections. We've just derived the pressure coefficient, which is the minus twice u prime, the velocity disturbance, and divided by the u infinity. Remember, this is on a small disturbance assumption. And at the very beginning of this lesson, we've derived the linearized compressible velocity potential equation. And do you remember originally it has 3 terms on the right hand side? If we are avoiding the transonic regime, the right hand side, all 3 terms can be deemed negligible. So that's why we have 0 on the right hand side. And now we are replacing the coefficient 1 minus m infinity squared by beta squared. So this linearized velocity, compressible velocity potential equation is like this. Okay. Now what we are doing is transfer xy, the old original coordinate system, into a new coordinate system, which is c and eta. And now we will see their relations. C equals x and eta equals beta times y. So this is pure mathematical transformations. Then we have the derivatives. If we see 0, which means, for example, partial x, partial eta equals 0 means x is perpendicular to eta. So they are not related. And also we have another 0, which is partial y, partial c. And this means c and eta are perpendicular to each other. So these are very important relation between the coordinate systems. And also we will define the new velocity potential in the new coordinate system, which is small phi, and they have this relation. And using this relation, we will use a chain rule to find the derivatives of, for example, partial phi, partial x, and partial y, phi, partial y. And since it's a chain rule, we also have the derivative of the coordinates, which are highlighted in red. And these red items can be replaced by the conclusions above. Okay, then the two velocity potentials, the relation between the two velocity potentials can be found. Okay, so finally we have partial small phi, partial c, and partial small phi, partial eta. So that's the relations. And also we have the highlighted portions, and they can actually be replaced by the derived results. Above, for example, partial x, partial c is 1, partial y, partial c is 0. So some of the terms can actually be eliminated. So let's move on. And finally, we have this partial phi, partial c equals beta times partial big phi, partial x, and then we have the other relation. This is first order. We can also have the second order relations. And since we have the original compressible velocity potential equation this way, and now we can actually replacing the big phi by the small phi. And then this is what we want to find. And this is actually the transformed velocity potential equation. And this is Laplace equation. And so if it's a Laplace equation and it's actually has features of incompressible flow, is that right? In the incompressible flow, the velocity potential equation is actually a Laplace equation. Okay, and this is very important. So with some transformations, transform the original velocity potential into a new coordinate system, and we can derive the Laplace equation. So this is very important conclusion. And so let's see how to move forward. We have the velocity potential, right? the pressure coefficient. And then, since the velocity perturbation u prime is defined by partial phi, partial x, so we just replace the u prime. And also we know in the new coordinate system, which is cosine eta, we have this relation. We can replace partial phi, big phi, partial x by 1 over beta times partial small phi, partial cosine. So we have this relation. And in the new coordinate system, also we can define the velocity perturbation, but this time it's in the incompressible flow. Since it's incompressible, you may notice the u prime here, the u is not inclined. So that's the difference between the compressible flow. Okay, so then we can rewrite Cp equals minus 1 over beta times twice u prime in the compressible flow, incompressible flow divided by u infinity. And now the twice u prime divided by u infinity is highlighted, and that's actually the pressure coefficient in the incompressible flow. So now we can find the relation between the Cp and the Cp0. Cp is the pressure coefficient in the compressible flow, which is at Mach number m infinity, and Cp0 is a pressure coefficient at the same location, but it's for the incompressible flow. So that's a relation. So why it's useful? Because if we know a pressure coefficient at a slow speed, which is equivalent, for example, 10 meter, 5 meter per second, which is equivalent to incompressible flow, because at that speed regime, the compressibility effect doesn't take, we don't need to take the compressibility effect into account at that low speed. So we can simply do a measurement, and then we don't need to do the high speed flow measurement, by just use this correction, and then we can have the estimate the pressure coefficient at a higher speed with compressible flow. So this is a very important pressure correction. Okay, so these are just some notations, and we call this the Prandtl-Glaude correction. So Prandtl, we are very familiar with his name, and Glaude is also English aerodynamicist, and so they derived this relation independently, almost at the same time. Okay, and so Prandtl-Glaude correction can not only be applied to the pressure coefficient, but also the lift coefficient and the moment coefficient, and they share the same format and a correction coefficient. Okay, and in here we have two examples, and I'm not doing it in here, but you can practice yourself. Okay, so apart from the Prandtl-Glaude correction, we also have the common chain correction or common chain rule, and which is slightly more complicated than the Prandtl-Glaude correction. And we also have even more complicated ones, which is Layton's rule. And okay, so these are the two we call them improved compressibility corrections. And actually, this curve is interesting. It compares the three compressibility correction methods, and we can see they stay at different heights, especially once goes to the higher Mach number. And for the same Mach number, usually the Layton's rule has lowest, remember, lowest pressure coefficient, because again this time Cp is inversed. And so also the experimental information, experimental data included. We can see in the Mach number regime range less than 0.6, the common chain rule is closer to the experimental data, and for the Mach number above 0.6, and we can see the experimental data actually stays between the Layton's correction and the common chain correction. And the pronto-glotte correction is less accurate when the Mach number is higher than 0.6. I would say it's significantly smaller. Yeah. For example, at Mach number 0.6, the common chain row gives a result of CP minus 1.3, but the pronto-glotte correction only gives minus 1.1. So there is a big difference. Okay, so these are the photos of these four important persons. The first is Hermann Glotte, and actually he died at a very young age, in his, if I remember correctly, in his 50s, and due to an accident. And the next three persons are actually in the same academic family. So Ludwig Pronto is the first generation, and then Theodor von Karman is his student, and Chen is also von Karman's student. So you see the continuation of the aerodynamic study in that group.